In this video, we're going to be looking at sections 16.7 and 16.8. In section 16.7, we'll be talking about weak bases. And so these weak bases, like ammonia, when we put them into water, they will dissociate to some extent to produce the conjugate acid of that weak base and the hydroxide ion. Just like with acids, we can write equilibrium constants and equilibrium constant expressions for them. So the equilibrium constant expression for ammonia would be equal to the concentration of ammonium times the concentration of hydroxide divided by the concentration of ammonia. We do have a value for these. We can get that value in Appendix D2, which I'm going to show you very quickly. So here is Appendix D2, and you'll see that we've got some equilibrium constants, Kb, for a bunch of bases. And you'll see I've selected the one for ammonia. Ammonia is 1.8 times 10 to the negative 5. Now, we'll find that there are two types of bases that we're interested in. One is going to be neutral bases, like ammonia, like the one we just looked at, where there is a non-bonding pair on one of the atoms. Usually it's on nitrogen, but it technically can be on other things as well. And that lone pair or that non-bonding pair of electrons can react or accept an H+, so it can act as a Bronsted-Lowry base and accept the H+. All of these are going to have expressions that look like this, where B will be equal to the concentration of the conjugate acid of your weak base times hydroxide concentration over the concentration of the weak base. We do have the table of values in Appendix D2, which I just showed you a minute ago, that shows you a whole bunch of these. The other type of weak base that we will have is anions that are the conjugate bases of weak acids. So the conjugate base of a weak acid is a weak base, and we can write this. So Kb is equal to the concentration of our conjugate acid times hydroxide over the concentration of our anion. We don't have a table with Kb values for these. For this, we'll have to use the Ka value of the weak acid, and I'm going to show you how to do that in section 16.8. So here is a short list of weak bases. Some of these are some of the nitrogen bases that I just showed you on Appendix D2, but some of them are the anion type. So here's HS minus, that we have carbonate, hypochlorite. Those are all examples of things that act like bases. Just like with Ka, the larger the value of Kb, the stronger the base. So all of these do count as weak bases, but the bigger the value, like this one for methylamine here, is 4.4 times 10 to the negative 4. That is the strongest on this list. The weakest on this list is this one, the C5H5N, which is called pyridine, in case you're curious. That one is our weakest of these bases. Now, just like with the acids, we can do calculations with weak bases as well. We can calculate the pH of a weak base using Kb and the concentration. We're going to do one. This one is done in the book, but I like to do it on the overhead just to show you what it looks like. So we want to calculate the pH of a 0.15 molar solution of ammonia. Well, the first step whenever you're doing one of these pH calculations with a weak acid or a weak base is to write out the equilibrium reaction. So here's the equilibrium reaction. We saw this one a few minutes ago. Ammonia plus water gives us ammonium ion plus the hydroxide ion. We're going to be using a concentration table, just like we did with weak acids. And in that concentration table, we will put the initial concentration of ammonia here. Again, this should look very familiar. In fact, you will get to the point where you can do these very, very quickly. But our original concentration, initial concentration of ammonia, water we can ignore because water is the solvent. Ammonium ion and hydroxide ion, both of their initial concentrations are 0. I mentioned this earlier, but in all of our chapter 16 problems, we'll see that our initial values are 0. Once we get to chapter 17, in fact, the whole point of chapter 17 is what happens when some of these aren't 0. For our change line, we'll see that this one decreases by x, and these both increase by x, and that gives us equilibrium values of 0.15 minus x, and that these are both x. Okay, now that we have the equilibrium values in terms of x, we can take those and put them into the expression. Again, our expression is going to be concentration of ammonium times hydroxide over concentration of ammonia. So there is our expression. Our equilibrium constant, this comes from Appendix D2. We also saw this one a minute ago. And then here again, ammonium is equal to x, hydroxide is equal to x, and the ammonia molecule is 0.15 minus x. And so we've got all of those there. So now we have a quadratic equation. And we have the same rule that we had previously, and that same rule is if our concentration is at least 400 times larger than our Kb, in this case, it was Ka when we did acids, but Kb now, then that means it's okay to neglect X. What that 400 does is that ensures that X is no bigger than 5% of the 0.15. So we're going to test that. I'm going to very quickly go over to my document camera and show my calculator. So here is my calculator, and we're going to put in 0.15 divided by 1.8 times 10 to the negative 5, and you'll see we get 8,333. That is definitely bigger than 400, so that means it's okay to neglect X. So now we're going to neglect X. We're going to neglect it all over the place here. So okay, so there is our equation. We're going to go ahead. I'm going to get out my red pen of neglect that X. And now we've got a fairly simple quadratic equation to solve. We'll cross multiply these. And so when we cross multiply them, 1.8 times 10 to the negative 5 times 0.15 gives us x squared. We multiply those together, and we'll get 2.7 times 10 to the negative 6. And then finally, when we take the square root of this, we will get 1.6 times 10 to the negative 3. Since X, this is a base problem, since X is the concentration of hydroxide, that means that we now have the concentration of the hydroxide ion. From that, we can take the negative log of that, and that will give us the POH. Now, I like to point this out when you're doing problems like this. Always pay attention to what it is that you're calculating. We've got hydroxide, so we can calculate POH. A common mistake here is to accidentally take the negative log of that and say, that's the pH. Well, if you do that, you're going to get a pH of 2.80, and that is definitely the wrong answer for a weak base solution. That if this were a pH, that would definitely be acidic. So what we want to do is to remember to subtract the POH from 14.00 to give us the value for the pH. And so there we get the value of 11.20. All right. Well, there's one more thing that I wanted to do, which is to do the percent ionization just to prove to ourselves that X really was less than 5%. We know that it was going to be because this ratio was greater than 400, but let's prove to ourselves that it really is less than 5%. So our percent ionization is equal to X over the original concentration. So X here was the 1.6 times 10 to the negative 3 0.15 was the original concentration of our base, and then multiplied by 100. When we do that, you'll see that comes out a little bit more than 1%, 1.1%. Okay, so now we are ready to do number 76. All right, so here is number 76. Okay, and I've got my document camera set up properly now. So we want to calculate the molar concentration of hydroxide ion in a 0.075 molar solution of ethylamine. There's ethylamine. It gives us a Kb value. That's a pretty big value for Kb. And we also want to calculate the pH of that solution. So very similar to the problem we just did on the presentation. So the first step is going to be to write out the equilibrium reaction. And then right below that, so leave room right below that to write a concentration table. So C2H5NH2AQ plus H2O liquid, and that's in equilibrium. I'll go ahead and write the conjugate acid of this. So C2H5NH3 plus AQ, and then the conjugate acid or conjugate base of water is the hydroxide ion. So we'll want this as a concentration table, initial, change, equilibrium. And just like what we have seen, our initial concentration of this is given here, so 0.075. Our initial concentration of the ethyl ammonium, so this is ethylamine, its conjugate acid is called ethyl ammonium, that one is 0. And the initial concentration of hydroxide is also 0. These will change. This one has to go down and these have to go up. So this is going to be minus x. So 0.075 minus x. And these, of course, will both be plus x. So we'll get x and x. Well, now let's write our Kb expression. And that's the concentration of C2H5NH3 plus times the concentration of hydroxide divided by the concentration of C2H5NH2. All right, we already know the value of Kb. All right, our value of Kb is 6.4 times 10 to the negative 4. So we'll take these values in terms of x and put them into the expression. So 6.4 times 10 to the negative 4 is equal to x times x, so x squared over 0.075 minus x. Well, now what we want to do is we want to determine, is it okay to neglect x? Because that's real. We prefer to neglect x when we're doing this because it makes it an easier problem. So we're going to see, is it okay to neglect x? Well, we'll take 0.075 and we will divide that by 6.4 times 10 to the negative 4. And if you're doing this along with me, you will see that is not bigger than 400. What that means is that x is going to be greater than 5% of the number that we are subtracting it from. That means technically it is not okay to neglect x. So we're not going to neglect x. We're just not going to do it. Instead, we're going to use the quadratic formula. And I know that's not as fun and as exciting, but we can do it. So let's cross multiply. So 6.4 times 10 to the negative 4 times 0.075 minus x is equal to x squared. Well, let's go ahead and distribute this. So 6.4 times 10 to the negative 4 times 0.075. So 6.4 times 10 to the negative 4 times 0.075, and that gives us 4.8 times 10 to the negative 5. All right, so 4.8 times 10 to the negative 5 minus 6.4 times 10 to the negative 4x, and that's equal to x squared. All right, let's move these two things over to the other side of the equation. In other words, we're solving for 0, and once we solve for 0, that tells us where, since this is a quadratic formula, it tells us where that parabola crosses the y-axis, the x-axis, and since it tells us where that is, it gives us the solutions to x. So we will get 0 is equal to x squared, and then this is negative, so we're going to add it to both sides, so that will be plus 6.4 times 10 to the negative 4x, and I'm going to put the x here in parentheses just to make sure that we know this is our coefficient, and that's x. And that this, since this is positive, when we move it over to the other side, it's going to end up being negative, so minus 4.8 times 10 to the negative 5. So that means that I'm going to go ahead and write this out. A is equal to 1. B is equal to 6.4 times 10 to the negative 4. And then this is important. C is equal to negative 4.8 times 10 to the negative 5. If we accidentally forget to put that negative here, we're going to get imaginary numbers when we do our quadratic formula. And I don't think we want to get those imaginary numbers. So just as a reminder, our quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So now we'll put these numbers in, and I am only going to put the plus in. If we put the negative, if we use the negative, we're going to get a negative value, and we saw that in the previous section when we were talking about acids. But we don't want a negative value for the concentration, so I'm only going to do the positive one. So x is equal to negative 6.4 times 10 to the negative 4 plus the square root of 6.4 times 10 to the negative 4 squared minus 4 times 1 times, and c is negative 4.8 times 10 to the negative 5. All right, and then we'll put all of that over 2 times 1. Okay, so we'll put all of those numbers in. Again, just to be clear, we're doing just the positive. Again, if we did the negative, we would end up getting a negative value for x. We don't want any negative concentrations. So, negative 6.4 times 10 to the negative 4 plus, and I'm going to put this in parentheses, and the square root of 6.4 times 10 to the negative 4 squared minus 4 times negative 4.8 times 10 to the negative 5, close parentheses, and close parentheses. I don't think I needed that extra parentheses, but all right. So we close the parentheses. That is the entire value that is up on top, and now we're going to divide that by 2. 2 times 1, and we get a value for x that is equal to 6.6 times 10 to the negative 3 molar. Since x is the value of hydroxide ion, we're going to put that as the value of the hydroxide ion, and that means that our POH is equal to the negative log of 6.6 times 10 to the negative 3. All right, so I'm just going to do negative log of our answer and we get 2.18. So 2.18. I suppose it is possible that if you didn't round, let me see, 6.6 times 10 to the negative 3. All right, so there's the 6.6 times 10 to the negative 3. And now we're going to take the negative log of that number. It's still 2.18, so it doesn't matter if we rounded it or not. So 2.18 is the pOH. Remember, we were looking for the pH. So pH is equal to 14.00 minus 2.18. So 14 minus 2.18, and that gives us 11.82. 11.82. Now, you'll see on this we had extra work to do because we had to multiply this out, turn it into a quadratic equation, use our quadratic formula, enter all those things into quadratic formula, and then come up with our answer. I'm going to promise that for your exam, I will not make you do one of these where you have to use the quadratic formula. You are always welcome to use your quadratic formula, but I am not going to force it on you. So just keep that in mind. You should be able to figure it out properly even if you don't use the quadratic formula. And in fact, let me show you something. Let's take this. So 6.4 times 10 to the negative 4, 10 to the negative 4 is equal to x squared over 0.075 minus x. Well, let's just for a moment go crazy and neglect that x anyway. All right, so if we neglect that x, then we're going to get this. We'll get x squared is equal to 0.075 times 6.4 times 10 to the negative 4. That gives us a value. Here, I'm going to flip this over to the other side real quick. That gives us a value. All right, so that gives us a value of, what would that be? 4.8 times 10 to the negative 5. So 4.8 times 10 to the negative 5 is going to be, that's the value that we get after we multiply those. Let's take the square root of that answer. And that means our x value here comes out to 6.9 times 10 to the negative 3 molar. You'll see that's definitely different than the value of x that we got here. On this one we got 6.6, here we've got 6.9. If that's equal to the concentration of hydroxide, and then we're just going to take the negative log of that, so pOH is the negative log of our answer, 6.9 times 10 to the negative 3. So I'm going to do negative log of our answer. That gives us a pOH equal to 2.16. And that gives us a pH, so 14 minus 2.16. That gives us a pH of 11.84. Well, you can see 11.84 is here, 11.82 is there. So even though our ratio was less than 400, it was like 117 or something like that. So it was less than 400, and even though that means that x is greater than 5% of this number, even when we neglected it, we still came out only 0.02 pH points away from the correct answer. Well, here I'm going to make another promise to you, and that other promise to you is I will not give you two answers on the test that are 0.02 pH points apart. So if the answer is supposed to be 11.82 and you come up with 11.84, you're probably correct. So I'm not going to give you choices like 11.80, 11.81, 11.82, 11.83, and 11.84. And the reason I'm not going to do that is because I am not a monster. There you go. I'm not a monster. All right. Well, let's go back to the presentation and look at the relationship between the Ka of a weak acid and the Kb of the conjugate base. This relationship is pretty easy to do. Let me show you how this works. So let's write out the equilibrium constant expression for a weak acid and for its conjugate base. So here is the equilibrium reaction for HF. I'm just going to use HF as an example. So HF plus water gives us hydronium plus fluoride. Easy. We can write out the equilibrium constant expression, the Ka for that, hydronium times fluoride over HF. Hopefully at this point you can do this really easily. You can even do that in your sleep. Maybe not perfectly in your sleep, but you get the idea. Now let's look at this next one. We're going to take fluoride ion, have it react with water, and when it reacts with water, a little later we're going to see that this is called hydrolysis. The reaction of an anion with water is called hydrolysis. So fluoride reacts with water, it does give us HF and hydroxide ion, and the Kb for that is HF times hydroxide over the fluoride ion. Well, we're going to take the expression for Ka and the expression for Kb and multiply them together. So when we multiply those two expressions together, Ka times Kb is equal to this whole thing. So hydronium times fluoride over HF times HF times hydroxide over fluoride. Well, you can see that we can cancel out the fluoride ion and the HF. That leaves us with the concentration of hydronium times the concentration of hydroxide. Now, I'm going to pause. I want you to pause the video for a second and think, what does hydronium times hydroxide equal? Okay, hopefully you paused the video and you figured it out. Hydronium times hydroxide, that's equal to Kw. We've seen this before. So that means that Ka times Kb of its conjugate base is going to be equal to Kw. Very, very useful tool. And that's why we can use Appendix D1 that has the Ka values for acids to determine the Kb for its conjugate bases. Let me show you a couple more examples of this. This is just a very short list of some acids and their conjugate bases. For strong acids have very large dissociation constants, Ka values that are greater than 1. And that means that their bases are such weak bases that they have negligible basicity. So like nitric acid, nitrate just doesn't act as a base at all. However, for the weak acids that don't dissociate 100%, we will find that their conjugate bases are going to be weak bases. The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. Now, if we get all the way down to something that is not really acidic, like OH minus hydroxide, well, its conjugate base is going to be a really, really strong base. So, this will get protonated essentially 100%. Well, let's look at number 82, and that will wrap up section 16.8. So we're going to look at number 82. All right, so here is 82. All right. Given that Kb for ammonia, here's ammonia, is 1.8 times 10 to the negative 5, and that for hydroxylamine, HO in H2 is 1.1 times 10 to the negative 8. Well, given those two numbers, which one is the stronger base? Well, clearly it is ammonia. NH3 is the stronger base, and that's because its Kb value at 10 to the negative 5 is greater than the Kb value for hydroxylamine. So ammonia is the stronger base. Which one is the stronger acid? Ammonium, which is the conjugate acid of ammonia, or hydroxyl ammonium, and here is hydroxyammonium. It is the conjugate. It is the conjugate acid of hydroxylamine. Well, if ammonia is the stronger base, that means the stronger conjugate acid has to be the other thing. So hydroxylamine is going to be the stronger acid. So hydroxylamine will be the stronger acid. Now let's calculate the Ka values for these. Well, Ka times Kb is equal to Kw. That means if we want to calculate Ka is equal to Kw over Kb. So the Ka for ammonium, and I'm just putting the ammonium there so we know which one we're talking about, is going to be equal to Kw, which is 1.0 times 10 to the negative 14, that's Kw, and then the Kb for ammonia, which is 1.8 times 10 to the negative 5. All right, so we'll do 1 times 10 to the negative 14, and we will divide that by 1.8 times 10 to the negative 5. And the number that we get there, 5.555, so we're going to call that 5.6 times 10 to the negative 10. And that's our value for Ka of ammonium. For Ka of hydroxyl ammonium, so HONH3 plus, that is going to be equal to 1.0 times 10 to the negative 14 divided by, and here we've got 1.1 times 10 to the negative 8. All right, so 1 times 10 to the negative 14, and we want to divide that by 1.1 times 10 to the negative 8. And we are going to get 9.1 times 10 to the negative 7. And you'll see that we have proved what we stated in part B. Which one is the stronger acid? Well, the stronger acid will be the hydroxyl ammonium ion. And you can see there is the Ka value for hydroxyl ammonium, and there is the Ka value for ammonium ion. All right. Well, let me make sure here. All right, yes, so that is the end of this particular video. Our next video, we will be starting on section 16.9.